Hello students, welcome to EPG Pathshala. I am Mohan Chand Joshi, Assistant Professor from Jamia Millia Islamia. Today we are going to discuss about a module, microscope based imaging and its application, part B, under the paper Genetic Engineering and Recombinant DNA Technology, part 1. So the learning objective for this module is that by the end of this module, students will understand what is light microscopy or optical microscopy. We'll get a brief overview about different kind of light microscopy such as bright field, dark field, polarizing microscopy, phase contrast microscopy, and differential interface contrast microscopy. We'll also get a brief introduction about how electron microscopy works, as well as about two more techniques, which is SPM and SNOM microscopy. In the end, we'll summarize all these light microscopy as well as electron microscopy to explain what are the usage of these microscopy. Light microscopy. So light microscopy is the also known as optical microscopy. It is used in which the visible light is used to illuminate the sample and then magnify a smaller object. The design for an optical microscope, as I also mentioned in the previous module, can be very simple or the complex. It can be very complex depending upon the requirement in terms of resolution, magnification and the contrast. And as I said, in a simple microscope that was used in the very beginning had a single convex lens, but now we use objective lens which has more than 10 lens in combination that are used, so that we can get higher resolution and the better magnification. There are different variants of microscopy that are available, and all of these are depending upon the sample that we want to visualize can vary. And in optical microscopy we use the light which is used for this illumination of the sample and modulates it to get a better contrast. And in the end, in optical microscopy or the light microscopy, we can visualize the sample either through a naked eye or can actually visualize it or capture it under the microscope. Bright field microscopy. So this is the commonly used method through which a sample is viewed, and it is available with most of the microscope right now, because you need to first visualize where exactly your samples are, and using this technique one been able to do that. And how it happens actually? So once you have put your samples in a cover slip on a slide and put a cover slip on it, now you illuminate that sample using a transmitted light. What happens in that case? The light is getting absorbed by the samples, and then you can view it through the objective to your retina or to your eyes. Now how the imaging is done in this case? Once you illuminate the sample, the light which is transmitted through the sample will get absorbed by the sample due to its differential refractive index in each area. So what happens in this case? You get a contrast, you get a dark imagery in a white background because the light is getting illuminated from the bottom. Dark field microscopy, a bright field image which I mentioned earlier, which is produced in a bright background, you have a dark image. Similarly, a bright field can be adapted to generate a dark field microscopy based imaging method. What is done in this case, that on your condenser you block the light by putting up a disc there. Now what happens in this case? The light gets reflected or refracted from the sample and it generates the image. The magnified image which you see in your microscope or through your eyes is actually a bright image, and it is produced in a dark background. As you can see the image which is shown in the further slide, that compared to bright field, the dark field will have the entire background is dark, but your image is bright. And what is the advantage of this technique is that it allows you to get a better viewing of internal structure, and also you can get it done in a live cells. You don't have to do any staining. Just by using this approach, you get a better understanding and a better resolution of internal internal structure of eukaryotic cells. Phase contrast microscopy. Now in this type of microscopy, as the name also indicates, there is a contrast in the phase through which the sample is illuminated. The phase contrast, it allows differentiation between different internal structure of a living cell based upon the different refractive index. within the cell, each organelle acts as a different organelle, and depending upon its own composition, it has its own differential refractive index. So when the same light falls upon two different organelles, depending upon the complexity and the compaction of the organelle, the light is diffracted and refracted in different way. So the underlying principle in this is that the light which is incidenting, that is hitting the sample, and the one which is coming out from the sample is out of phase. So because it is reflected through different part, it has it and with a different diffractive index, so they are out of phase. By using the phase plate, we can sync them, we can bring that out of phase light into the phase again, back to phase, and visualize it. Thereby we are getting a higher resolution image. So as you can see in this picture, we have a phase ring, we have a condenser through which the specimen is illuminated, and you can see the light is entering into a different phase. But once it is hit the specimen and gone through the objective lens, it is out of phase because it deviated from the origin of where the light was incidented. Then by using the phase plate again, we can bring that light back into the phase, and in this way we can see the difference in the complexity of the sample, but just by looking at the difference in the transmitted light phase. Polarization microscopy. In polarization contrast microscopy, in this the sample is illuminated with a polarized light, and the polarization light have a different vibration. So when the sample alters the polarized light, the altered light is allowed to pass through an analyzer, and that analyzer allows us to bring that polarization light back into the same vibration and same polarization, so that it can be visualized. And in this case, the magnified light, the image is produced in a dark background, but by putting a polarization plate or a lambda plate, we can also inverse the color and get our can produce a generator colored image. This microscopy is been used to visualize crystals as well as polymers. Differential interface contrast microscopy, DIC. This is used in combination with bright field microscopy. Also, we get a different add-ons with compatible with different objective lenses, and this is called DIC. And DIC improves the contrast, as it is also improves the overall quality of a bright field image. This is also known as Nomravsky microscopy. In this, sample is illuminated from a polarized light, set of prism as well as filters are used, so that these different phase light can be synchronized and can be used to generate image, and the resulting image is also high contrast image. So we discussed about all these different kind of variants of light microscopy, and here is an example how a representative image looks like. In the very first picture, you see a picture which is generated by the bright field microscopy, and you can see the entire background is white, and there is a contrast difference between different cells. So this is a cell line image, and you can see we have been able to differentiate the structural internal organs and internal structure of within the cell. Then we have DIC, which produce a very high quality image. Phase contrast also provides a very high contrast in a darker background. Dark field microscopy, the object is whiter and the background is dark because we have a plate which is placed before the condenser, and the polarized light using in combination with the lambda plate, and you can see we get a colored image. So these are the variation that we use by manipulating the illuminating light source. Electron microscope. Now in electron microscope, instead of using light as an illumination source of illumination, here electron beam is used to illuminate the sample. And this is also, in this microscopy technique, the beam of electron is transmitted through the sample, and because it interacts with the sample, That's why the sample information is transmitted in terms of in different contrast. The electron beam is accelerated from the source of illumination, that is electronic gun, and then shot at the sample. Wavelength of electrons are 100,000 times shorter than the visible light, thereby it provides it a very high resolution. There are two variants of it, SEM and TEM. The light microscope is used for live as well as fixed cells, but electron microscopy is basically used for the fixed cells, and the resolution of light microscopy is 200 nanometer, while in this it will very higher. And as you can see in this picture, once the electric beam is hitting the sample, it creates various energy gradient, and which results in the electrons which are transmitted and can gives you more information. All these transmitted and the scattered electrons, secondary electrons, can give us more information about the sample structure and its elasticity and its overall composition. As mentioned earlier, transmission electron microscope is actually the simplest form or the very first form of the electron microscope. In this case, electron used as a beam. So for illuminating, instead of using a light, electron beam is used for illuminating. Now, so the basic outline of a transmission electron microscope includes an electronic beam that need to be generated from an electron gun. So the way it works is that electron gun generates the electron beam. Now using the anode, it is accelerated and also directed toward the sample, and the sample has to be ultra thin. It has to be very thin, approximately 100 nanometer or even less, so that it can be illuminated and can be better viewed. So now the electron beam that has been generated directed by the anode is further focused by the electrostatic or electromagnetic lens, which allows it to direct on the sample. Once the light or the electron beam has been shot, or once it hit the samples, what happens, the image is transmitted, the image is formed by a transmitted beam of electron which are interacted with the samples, and the transmitted light again is magnified by the objective lens, because in this case the electrostatic lenses or electromagnetic lenses creates a convex lens which allows you to further magnification, which will be explained in next slide as well. So now this transmitted light is magnified, and then that image it can be captured by either through your eyes or can be attached to a camera where it can be captured. Now as I mentioned earlier, because this electron beam is hitting the sample and transmitted light is making an image, so the sample is actually fixed in this case. That means the cells, you cannot view a live cells, that the cells are dead because you are hitting it with a very high voltage of electric beam, but the resolution that you get in this case is very high. One of the component of the electron microscope is the vacuum system. The vacuum system is very critical for the microscope, because when the high voltage electron beam is passed through the system, it has to travel in a vacuum system, otherwise it can result in an arc as well as in a short circuit. The TEM imaging, and therefore it is performed under very low pressure, 10⁻⁴ Pascal, and what it allows is to improve mean free length. The electron interacts with the gas, and if we are using high voltage TM, then it is also required that we match up with the very low pressure also, so we can go to 10⁻⁷, 10⁻12. It allows that voltage difference between cathode and the ground stage without generating any kind of arc, as I mentioned earlier also, and the collision frequency between electron and gaseous atoms is reduced to minimal. So if there is medium other than the vacuum, what will happen, the electron will interact with it and will give us a false signal or the lots of background noise, which is not good for the sample resolution. Specimen stage. Now this is made up of copper, molybdenum, or gold or platinum, and as you can see in these two pictures, on the right hand side we see the grid which is in which the sample is kept. The sample has to be ultra thin. It should be around 100 nanometer in width so that it can be properly visualized and that electrons can pass through it easily. Thicker sample will have a problem in terms of the resolution because most of the electrons might get just trapped inside the sample and would just provide a dark black image instead of giving us a high resolution image. The specimen stage is kind of it looks like this, where we have the vacuum rings. As we know that inside the system is vacuum tight, so therefore sample is put in the grid as shown in this picture, and then these two rings ensure that vacuum is maintained inside, and the sample is put on this grid, and that grid is kept in that stage, and then the stage is pushed into the under the microscope, in which the electron beam will directly hit on this grid containing the sample. Electron gun. As the source of illumination in electron microscope is electron beams, therefore this electron gun is used to generate the electron beam. It requires the filament, a biasing circuit, a well-nut cup, and an extraction anode to generate the electron beam. As you can see in this picture, we have a filament, we have a well-nut cylinder which is negatively charged, and once the filament is connected to the negative component power supply, electrons are pumped through the electric gun, and then there are anode which are helped to accelerate it as well as to direct the electron beam towards specific direction. The well-nut is designed, currently designed in such a way that it has more negative charge on it, so that we can we can focus the electric beam toward the anode directly instead of getting it discharged within that cylinder or getting spread out within the cylinder. Electron lens. So the microscopy lens through which the electron beam is passed, it is very critical for the resolution as well as the contrast of EM imaging. Is actually made up of yoke and electromagnetic coils, pole pipes, and external control circuit as shown in this picture. So the electromagnetic coil which generates a convex lens like configuration so that we can magnify the image. The coils are located within the lens yoke and contain a variable current, and coil also utilizes high voltage, and therefore it requires, because it utilizes the high voltage, therefore it requires a very high insulation. If it is not highly insulated, it might result in the arc. Aperture. These are metal annular plates placed at the fixed or movable optics so that allow the passage of beam through the one axis only, and this aperture size can be manipulated. That's why we can manipulate the intensity of the electron beam that are passing through the sample, that are passing through the aperture. It is very also important so that any scattered beam which is resulting from the sample is prevented from going back to the objective lens and getting imaged. Scanning electron microscope. Similar to TEM, scanning electron microscope is another variant of electron microscope in which electron beam is used to illuminate. However, in this, instead of looking at the transmitted light, in this case the scattered light is used to generate a image of a sample. So when an electron beam is bombarded on a sample, the loss of energy due to interaction between sample and electron beam results in a heat, emission of low energy secondary electron, as well as the high energy back scattered electrons which are emitted, and these electrons which have the information about the sample and its composition in terms of structure and topography are captured, and that's why this information is taken and to generate a three-dimensional image. And remember, because these scattered electron and the signal is coming with a differential intensity because the interaction is very differential depending upon the sample, the thickness and the composition of the sample. That's why scanning electron microscope in compared to transmitter electron microscope provides a better resolution in terms of the structure and topography. This technique is used to generate a three-dimensional image of the sample as well. Comparatively it is slow, but the image generated by this one is in higher resolution compared to higher resolution in terms of its spatial resolution is higher than the TEM. So as we discussed about SEM, TM, so both form electron microscopy has certain variation and differences among themselves, and that's what is been tabled in this, has been catalogued in this table. So as I mentioned earlier, SEM actually the image is formed based upon the scattering electrons that we are getting once the electronic beam, when the electronic beam hits the sample. On the other end, in TEM we see the transmitted electron that are used to form an image, and the secondary, the scattered electron that are captured are producing the image instead of making a transmitted light or transmitted electrons. SEM actually focuses on understanding the surface and its composition. On the other end, the TEM gets the information what is inside the sample. As I mentioned earlier, SEM electrons are interacting with the surface and getting scattered, and the secondary electrons are captured by the machine. Also, the SEM is a slow process because it scans the entire samples compared to TEM. But SEM is very powerful in generating a three-dimensional image because we are getting a lot of information by capturing those scattered beam compared to TEM where we just get a two-dimensional image. That means we are getting information in terms of in X and Y. The resolution of SEM is around 0.4 nanometer, while TEM gets a very high resolution of up to 0.5 angstrom. And similarly, magnification can go up to 2 millions in SEM, while in TEM we can get up to 50 million x magnification. So both of these techniques have their advantages and disadvantages, but depending upon the application that researcher is interested in, they can either opt for SEM or TEM. Scanning probe micro-based microscopy is a separate method. It's a different method than the light microscopy or the electron microscopy that we discussed. In electron microscopy and the light microscopy, the sample is illuminated either with using electron beam or using the light microscope as a source of illumination. However, in this, instead of illuminating it, sample is physically mapped, and the structure and the distribution of sample is physically mapped using cantilever tip. For example, in this picture, as you can see, laser is pointed toward the cantilever tip and the cantilever tip is scanning the entire sample. So depending upon the depth and the height at which the contact is made, that information is directed toward the photodiode, which is used to construct an image based upon the interaction pattern that cantilever experience. This mapping is very fine and can be very high resolution because the cantilever tip is moved using the piezoelectric system, whether it can be scanning or by a tapping mode. In both the processes through which it maps is highly motorized and highly controlled. That's why we can get resolution up to atomic level, and the capability of this system has been utilized in understanding in determining the structure of chromosome as well as in the physical samples or as well as the samples as well as different sample which is used in geography or in physical sciences as well. So this technique is very multidimensional and provides a very high resolution. Scanning near field optical microscope or SNOM. This microscopy allows a resolution, again very high resolution of 220 nanometer lateral as well as 2.52 vertical resolution, and this is based upon, because this microscopy exploits the evanescence wave nature, and evanescence waves are actually oscillating magnetic field which do not propagate. So if a evanescence wave is generated on the sample or within the sample, it will oscillate there, and the energy within that area, in confined area, can be used to generate a image of a high resolution image of our sample. In this, evanescent field is created for a sample when we focus our laser light and pass it through aperture which is smaller than the excitation wavelength. So what happens that we create a near field as well as a far field, and then we have created the evanescence field with which we can image our sample. And this this method is used extensively in turf, where the membrane structure and the membrane structure and organization is viewed at a very high resolution. In this, we discuss about the differences between the light microscope and the electron microscope, and this table also represents is just representing the fundamental difference that we have between light and electron microscope. First, the visible light that is used in light microscope compared to the electron beam that is used in microscope. Electron microscope is very different. Resolving power is very poor in light microscope but very high in electron microscope. We can achieve very high magnification again in electron microscope compared to this one. The light source again is different in both the cases. The lenses in light microscopes are glasses compared to the magnets in electron microscope. The interior in a microscope is air filled, and compared to the vacuum filled in electron microscope. And we can generate an image either on a screen or in a photographic film. In electron microscope, in light microscope, we can visualize it through our eyes as well. And one of the major difference between these two microscopy, that light will allow us to visualize fixed, that is dead cell, as well as the live cells, because the light which is illuminating the subject is sample is not toxic. But on the other hand, electron microscope can only visualize the fixed cell, that is dead cells, because it is beamed by the very high electron, which it is bombarded with a high voltage electron beam. So the student, by the end of this module, I hope you have understood that light microscopy is a very powerful tool in terms of visualizing a smaller object. Because we can magnify it in high resolution as well as get in high contrast. And as you must have learned, that there are several adaptations that has been made to light microscopy. Whether it is a bright field, dark field, phase contrast, or polarizing one, we have utilized the capability of the light, which is a wave, and how it can be used to visualize different samples to get more or different kind of information from each sample. Also, you must have understand the electron microscopy that has been used to get a very high magnification as well as higher resolution of the sample, and it also has two variants, SEM and TEM. Depending upon the application, we can use either of those ones. But the important feature is that in electron microscope, we use electron beam to illuminate the sample instead of using light as a illuminating source. And light microscopy will allow us to image both, whether it's fixed cells, that means the dead cells, or the live cells. But electron microscopy has a limitation because we are dealing with a very high voltage electronic beam. Samples has to be fixed. That means the samples are dead and they are fixed on a grid when we are visualizing it. Also, there are other techniques like surface probing based microscopy, SPM, which is also we know is atomic force microscopy, will allow us to give us a higher resolution at the atomic level also. But this technique is based upon probing the sample by using a physical cantilever. And also near field microscopy, which is also have one application in turf, which has been which uses evanescence wave to get a very high resolution in both X and Y as well as in vertical resolution. So as you can see, microscopy has several variants, and has been adapted over the years depending upon the requirement of the researcher as well as the kind of sample that we want to visualize. Microscopy has adapted from light microscopy, whether it's electron microscopy or many variations of fluorescent microscopy, which will be discussed in another paper or another modules. Thank you.